Welcome to my series on statistics. This course is going to utilize calculus, so it should serve as good supplementary material for any sort of university course in statistics. But at the same time, I'm going to emphasize theory and derivations of the ideas, explanations for the ideas within statistics, which I feel is usually ignored, especially at a beginner level within colleges and universities. And in order to actually make this course feasible, what I'm going to do is break up these topics into essentially two parts. So for each topic, there's going to be two videos. There will be one video that covers the theory behind an idea, where it comes from, derivations if applicable, and then the subsequent video would show how we actually work out problems of that nature. Because in general, the equations within statistics can get a little bit long-winded, mathematically complex, and they're not the sorts of things that you would be computing on a day-to-day basis with a whiteboard. They're probably something that you would relegate to a computer or a calculator. And so I'm going to show both sides of this. It's going to be where it comes from, how it actually works, the idea behind these statistical methods, and then the subsequent video is going to show how to actually utilize that and put it into practice. The former of which I feel like is very frequently ignored. And so without further ado, we're going to get started with a discussion of general probability. This can feel a bit dry, especially because some of it might feel like a recap from elementary school. So I'm going to try and brush through this as quickly as possible, but it is important to have a solid idea of probability before you start trying to understand statistics. So that's what we're going to do in this video. Hope you all enjoy the series, and let's get started. Right, so the question here is, what is probability? Probability is a measure in statistics that gives us the chances of a different outcome happening. And the way that we compute that to mathematical language is we take the number of outcomes involving A, for example, divided by the total number of outcomes, and that gives us the proportion of times that A would occur. Now, I want to make the point here. Here's an example of that. If you were to flip a coin and you want your probability of it landing on heads, there's the number of outcomes involving heads, that's 1, divided by the total number of possible outcomes, which is heads or tails, it's 2. So your probability of getting heads would be 1 over 2, which is 50%, or 0.5. Now, in real life, what you would be dealing with is, let's say, just as a silly example, you flip the coin, and you're standing over a volcano, and so it lands in the volcano and melts into its constituent pieces. That is a technical possibility, but when we're conducting statistics, we tend to ignore these possibilities with very, 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 very slim, negligible chances. And in theory, we're not dealing with that at all. We're dealing with a subspace of total possible outcomes. So when we say, what is the probability of a coin flip resulting in heads, we're dealing with the subspace of total possible outcomes of the coin flip. So that's just heads or tails, and that's all we're concerned with. So the probability of heads is heads, 1, the number of outcomes involving heads, divided by the total number of possible outcomes, 2. So that's where you get your 0.5 from. So one important aspect of probability is that if you sum up the probabilities of each of the possible events that can occur within a given sample space, which is what you call the set of all possible outcomes for a statistical experiment, that probability is going to be equal to 1. The reason being, if there's only n possible outcomes and you sum up the probability of each one of those, what you're going to wind up with from this definition is you'll get the number of outcomes involving A, but you'll add this up for all of the possible outcomes. What you're going to be left with is the total number of possible outcomes. And the denominator is going to be unchanged. It'll be the total number of possible outcomes. And so that is just going to be equal to 1. Another way to view this is if you flip a coin, for example, there's 2 possible outcomes, either heads or tails, and they make up for a fair coin. Each of them is going to take up 50% of the sample space because there's a 1 in 2 chance for each of those different outcomes. But those are the only 2 outcomes. So when you add them together, the probability of at least one of those events occurring, where you flip a coin and you either get heads or tails, well, that has to be equal to 100% because those are the only 2 possible things that can happen. So this is a property of probabilities. Now, another important property of probabilities is going to be the probability of one event and then another event occurring, which is denoted by this little upside down symbol U here, this upside down U symbol here called the intersection. The probability of one event occurring here, A, and then B, is going to be equal to the product of those probabilities. Now, an interesting question here arises, which is, why are we multiplying? And the reason for that is that is the only way to keep track of what our definition of probability tells us, which is that the probability of an event occurring is the number of outcomes involving that event divided by the total number of possible outcomes. And so just as an example to demonstrate that, let's consider the probability of rolling an even number on a dice and then rolling an odd number on the dice. So for the first part here, the probability of rolling an even number, that's going to be this right here, because you can roll a 2, a 4, or a 6. So there's 3 possible outcomes involving an even number divided by the 6 numbers on the dice. So your odds of rolling an even number is 50%. And then that's our first outcome, or our first statistical event. And so we're interested in what the probability is of rolling an even number and then an odd number. And so for each one of these outcomes, there's 3 of them. There are 3 possible odd numbers that we could roll. So let's say, for example, that we roll a 2. Then there are 3 different possible outcomes that are the actual outcome that we want. You could roll a 2 and then a 1. You could roll a 2 and then a 3. You could roll a 2 and then a 5. And so that gives us 3 possible outcomes that we want. The same is true for the 4. You could roll a 4 and then a 1, a 4 and then a 3, a 4 and then a 5. So there's 3 possible outcomes for each of these 3 possible outcomes. And the way that you calculate that is by multiplying them together. And so that gives us 9 desired outcomes here. And for the number of possible outcomes, there's 6 different possibilities in the first case, because you can roll 6 different numbers. And then there's 6 different possibilities in the second case. So there's a probability of rolling a 1 and a 1, a 1 and a 2, a 1 and a 3, etc. So there's 6 different possibilities for each different dice roll that you could get on the first one. And the number of possible outcomes there is the product of those 2. So that's going to be 36. And so this operation of multiplication is the only thing that allows us to keep our definition of probability consistent. It's what allows us to calculate the number of desired outcomes for 2 different events happening in succession while maintaining that number of possible outcomes in the denominator. So that's why we are multiplying probabilities together to calculate the probability of subsequent events. Now, the next question that seems natural to ask is, what is the probability of one event or another? And the way that we answer this question is we say that the probability of A or B, which we denote with this capital U looking symbol here called union, the probability of A or B is just going to be the sum of their probabilities minus the probability of both of those events occurring. Now, this factor right here might be a little confusing at first, and so I'll ask you to suspend your disbelief for now until about 2 minutes in the future when I'm going to explain geometrically how this all makes sense. But for now, let's look at an example. So if we want to calculate the probability of rolling a 1 or a 2 on a fair dice, then what's that going to give us? Well, the probability of that, let's just call it y, where y is the probability of rolling a 1 or a 2 on a fair dice. That's going to be the probability of rolling a 1, right? Which is just, well, there's 1 possible outcome involving a 1 and 6 total possible outcomes, so it's 1/6. Plus the probability of rolling a 2, and the probability of rolling a 2, there's only 1 possible face of the die that includes a 2, and there's 6 total faces, so it's 1/6. And what's the probability of rolling a 1 and a 2 on one dice roll? Well, that's not possible. You can only roll one different side is going to be what you get. You're not going to roll both in one roll. And so that is going to be equal to 0. And so when we add these together, we get 2 out of 6. So the probability of rolling a 1 or a 2 on a fair dice is 1/3, or 0.33, or 33.333%, however you want to notate it, but that is the probability of one or the other. So now I want to get into the business of explaining why we have this factor here that I've outlined in red. It doesn't seem intuitive at first. This is best understood geometrically. So I have a diagram here. In this diagram, this rectangle here represents the sample space, which, as I said before, the sample space is the total probability of all the possible outcomes of the statistical experiment. And so the probability of at least one of the possible outcomes of a experiment occurring has to be equal to 100%. There's a 100% chance that at least one of all the possible outcomes will happen. And so the area of this box here representing the sample space, representing the probability of at least one event in the sample space occurring, has to be equal to 1. And then within this sample space, I have two possible events here. There's event A and event B, and the area of these circles represents their probabilities. And so there's four possibilities here, really. There's the probability that A occurs, there's a probability that B occurs, but there's also the probability that A and B occur, which is represented by this overlapping region of this Venn diagram of the two probabilities. There's also the probability that neither one of the events occur, which is the rest of the area of this rectangle that isn't encompassed by these two probabilities. And so if we want to calculate what the probability of A or B occurring is, that's going to be the area of this region covered by both of these circles, which should be pretty intuitive. And what happens when we just naively sort of sum these areas together in order to try to calculate that region? Well, if I was to add this region to this one, if I just shade them in here, what you'll notice is that this region in the middle gets counted twice. And so if we want some expression that just tells us the probability of A or B occurring, we have to account for this, and we have to subtract off one copy of this middle region that gets shaded in 2 times. And so that's why in this formula up here, we are trying to calculate the probability of A or B occurring, which is that region of the graph encompassed by A and B. And so what we do is we add those two together, but we also subtract off one copy of that middle region so that it doesn't get counted twice in our formula. All right, moving along here, it's going to be important to mention this notion of mutual exclusivity. Mutually exclusive events in statistics are two events where the probability of both events occurring is equal to 0. In other words, if one event happens, then the other cannot. One example of this could be if you flip a coin once, what's the probability of getting heads or tails, or heads and tails? That probability is going to be equal to 0. You can only get heads or tails. You can't get both. And so the way that you would represent this geometrically is, suppose this is some sample space. It's represented by this rectangle. And there's the probability of A occurring and the probability of B occurring, represented by these two respective circles. What's the probability of A and B occurring? Well, as you can see, no region of the sample space is covered by the overlapping circles that represent the probabilities of both of these events. There is no region of this circle that represents the probability of A occurring that is also covered by that circle that represents the probability of B occurring. So the probability of both of these events occurring is equal to 0. So you could imagine that if you wanted to represent the sample space for a coin flip geometrically, it would look something like this, right? You would have the total probability, and you could just cut it cleanly in half, and one of these would be heads, and the other one would be tails. And there would be no region that overlaps, and there would be no region that is not encompassed by either event because one of them has to happen. And so that's what it means. That's what we mean by mutually exclusive events. They're events where only one event or the other can happen. Now, one of the last topics here is going to be that of conditional probability. And in order to introduce this, I kind of have a challenge problem here on the screen. It says if 70% of students pass Calculus 1 and 80% of students pass Calculus 2, what percentage of students pass Calculus 1 and Calculus 2? And I encourage you to pause the video and think about this for a second. I have the answer hidden behind this red block here, but this is something worth thinking about. So hopefully you've done that. And before I reveal this answer here, I want to give one more hint to see, because perhaps you have an answer in your head, and I just want to ask a question to see if that challenges that answer a little bit. Do you think that the probability of a student passing Calculus 2, given that they failed Calculus 1, would be the same as the probability of a student passing Calculus 2, given that they got 100 in Calculus 1? And so if that kind of cued you in here, the answer is that we don't know. The reason being is because these two events are not necessarily independent, meaning the act of passing Calculus 1 would kind of influence your odds of passing Calculus 2. The two events are somewhat connected, and the results of one event can help to sort of explain the results of the other event. And so we don't know what the odds of passing Calculus 1 and 2 are, because we only know the rough estimates, or the raw proportions of what students pass Calculus 1 and what students pass Calculus 2, but we don't know what percentage of students pass both, and we don't know what percentage of students failed both. And so let's get into this discussion to see how we can sort of navigate situations like this and deal with these types of problems. So in order to do this, I need to introduce some notation. So here I'm going to write the probability of A given B, and I'm going to notate it this way with this vertical bar. And so what this is this is the probability of A given that B has already occurred. And now I'm sure that you'll agree, if I take this probability and multiply it by the probability of B occurring, that will give me what? Well, that's going to give me the probability of B and the probability of A given B occurring. This is just going to be the probability of A and B. That's all that's going to be. Probability of A given B multiplied by the probability of B. Well, that's the probability of both events occurring, and that's just going to be the probability of A and B. And so this kind of gives us a method to deal with conditional probabilities, because we can algebraically manipulate this to tell us that the probability of A given B is going to be equal to the probability of A and B occurring divided by the probability of B occurring. And so this is where we start to talk about conditional probability. This is the probability of one event given another. And I want to sort of point out here what's going to happen if A and B are independent. And so I mentioned earlier, but the notion of independence tells us that one event does not have any sort of control over the other event. They're not connected in any way. That would be like flipping a coin. If you get heads on one turn, so to speak, or one experiment, it's not going to affect the outcome of the next experiment. You might get heads again, you might get tails, but whatever you got the first time does not influence what you get the second time. It's the same with the dice. This is not necessarily the case for events that are not independent. For example, like with the notion of passing Calculus 1 and Calculus 2, those are not independent events, because what you learn in Calculus 1 would get applied in Calculus 2, probably. And so those two events are not independent. So let's imagine that there are two independent events, like a coin flip, for example. Well, then what's the probability of A and B? They're no longer connected, so we could compute this. That's just going to be the probability of A multiplied by the probability of B, as we saw before. And what happens here is that the probability of B here in the denominator is going to cancel with it in the numerator. And what we're left with is that the probability of A given B is going to be equal to the probability of A, just outright, for independent events. And so this should make sense. But for events that are not independent, we're not going to know what this value is unless it's given to us. We're not going to know what the probability of A and B given to dependent events, to events that are not independent. And so for dependent events, for dependent or non-independent events, we don't know how to compute this value, how to compute this. And so we have this formula for conditional probability. The probability of A given B is the probability of A and B over B. And it does work for both independent events and non-independent events. Here in independent events, it's just going to reduce down to the probability of A, which is exactly what you would expect given the notion of what independence means. What's the probability of A happening if B has already happened? Well, B doesn't have any effect on A, and so for independent events, that's just going to be the probability of A, and that's exactly what we get. All right, so let's look at an example of conditional probability to sort of solidify that notion. Here we have an example where a student takes 2 courses. You can imagine this is Calculus 1 and 2. The probability that she passes the first course is 62%, and the probability that she passes the second course is 0.55. In addition, the probability that she passes at least one course is 90%. And so we're asked here to fill in the contingency table at the bottom. So we have this column here, which is the column where she passes the first course. There's 2 possible outcomes. She can pass the first course and pass the second, pass the first and fail the second. Then we have this column here, which represents the column where she fails the first course. Given that she fails the first course, she can either pass the second or fail the second. And the same is true with these rows here. And so if we want to fill in this table, we can't just say, well, the probability of her passing one and the probability of her passing the second are these 2 values here. So we just multiply them together to get the probability that she passes both. That's the wrong way to approach this problem because, as we showed in the last example, these events are not necessarily independent, and they probably aren't, especially when you're talking about passing a course. So how should we go about filling in this table? Well, the first thing to realize is that the probability that she either passes or fails the course is 100%. She's either going to pass or fail it. And so the probability that she passes is 62%, so the probability that she fails would be 1 minus the probability that she passes, otherwise known as the complement of the probability of her passing. And so 1 minus 0.62, that's going to be 0.38. And then here, the probability that she passes the second course is 55%, which means the probability that she fails the second course is going to be equal to 0.45. That's the probability here. These all have to add to 1 here. And now, what else do we know? Well, we know from the problem that the probability that she passes at least one course is 90%. And so what does that mean? Well, what is the probability that she passes at least one course? That's going to be 1 minus the probability that she fails both courses, right? The probability of failing both. Because when she fails both, that's the only situation in which she doesn't pass at least one course. And so 1 minus the probability of her failing both is equal to 90%. Well, what does that tell us? If you solve for the probability of failing both, we could just add that and then subtract 0.9 from both sides. And what we're going to get is that the probability of her failing both, which would be this column here, or this cell here, is going to be 0.1. And now we actually have enough information to finish filling out this table because this column here has to add to 0.38. If she fails the first one, the probability that she fails the second, given that she fails the first, is 0.1. But the probability that she passes the second, given that she fails the first, has to add to 0.38 because that's the probability that she'll fail the first course. And so that here is going to be 0.28. And now we have enough information to finish the rest. Here, this row has to add to 0.45, and so we'll get 0.35. And then here we have a choice. We can either take it from the column or take it from the row, but it doesn't matter. Either way that we approach the problem, we should get the same answer. And so I'll just go here. What is 0.62 minus 0.35? I don't know because I'm really bad at arithmetic, so I'm just going to write it down. 0.35. That's going to be 0.27. And if we've done our work here correctly, what we should notice is that in the problem here, it says that the probability that she passes at least one course is 90%. And what is that on this diagram? Well, here's the probability that she passes the first and fails the second, but she passed at least one. Here's the probability that she passes the second and fails the first, but that still she passed at least one course. And then here's the probability that she passes both of them. And so these three if we add them all together, should represent the probability that she passes at least one course. So we could check our work here. If we add these all together and they equal to 0.9, then we'll know that we've done the problem right. And if you add all three of these values together, 0.27 plus 0.28, that's going to be 55 plus 0.35, that's going to be 0.9. So it at least appears that we've done this correctly. And so this is an example of a conditional probability problem. You have to be very careful not to apply these rules of probability that are only valid when you're dealing with independent events to situations where events are not necessarily independent. This is something to be mindful of, not just in your coursework, but in real life when you're trying to apply the principles of statistics. All right, I've got one more problem here for conditional probability that's going to touch on something called Bayes' theorem. But Bayes' theorem, I don't think it's actually necessary to learn it. I think it's just best to understand through example, and that's going to make more sense after we do this problem. So suppose there exists a test for AIDS that is 99% accurate and that there's a high-risk population with a 10% chance of having AIDS. If a member of this population gets a positive test result, what are the odds that she or he actually has AIDS? And so this is an interesting problem because you can imagine that in real-life applications, any sort of test for disease, any sort of test within some sort of engineering field or whatever you might be interested in, those tests are never going to be perfect. So here we have a test that's 99% accurate, and what we're asked to compute is the probability that our member of this population here has AIDS, our probability of AIDS, given that they have a positive test result. And so we know from our understanding of conditional probability that the probability of A given B is going to be the probability of A and B, so the probability of AIDS and a positive test result, divided by the probability of B, which in this case is the positive test result. And so the numerator here is pretty easy to compute. What's the probability of having AIDS and a positive test result? Well, it says that the test here is 99% accurate, right? So if you have a 10% chance of having AIDS, and there's a 99% chance that the test is accurate, the probability of you having AIDS and a positive test result is going to be 0.99. The probability of it being a positive test result multiplied by the probability of having AIDS, so 0.1. Now the denominator here is going to involve a bit more thinking, because what are the possible ways that we can have a positive test result? Well, there's the probability that we have AIDS and the test is accurate, right? But there's also the probability that we don't have AIDS and the test is inaccurate. And we have to consider both of these possibilities because in both of these situations we will get a positive test result. And so the probability of getting a positive test result is going to be the sum of these two probabilities here. The probability of having AIDS and the test being accurate and the probability of not having AIDS and the test being inaccurate. The probability of having AIDS and the test being accurate is that 99% accuracy multiplied by the 10% chance of having AIDS. And the probability of not having AIDS here would be 90% multiplied by the 1% chance that the test is inaccurate, right? So that would be that false positive, 0.01. And that's kind of bleeding off to the side of the screen here, but I'm going to rewrite it there. Here we're going to get 0.99, 0.1. It's the probability of you having AIDS and the test being accurate, so you get a positive test result. But there's also the probability that you don't have AIDS. There's a 90% chance of that, multiplied by the probability of the test being inaccurate, a 1% chance. And so both of these results here will give us a positive test result. And so when you actually compute this, plugging into your calculator, what you'll get is approximately 0.9167, or 666 repeating. And so what this tells us is that, like, even if you're in that high-risk population, and even if you have the test that's 99% accurate, if you get a positive test result, you're still only a 91% chance that you'll have it roughly. There's that 10% chance of a false positive. And this is how actual drug companies, actual cancer diagnoses, and things like that are computed, they're done with this sort of idea of conditional probability, which is based on something called Bayes' theorem. That was this idea up here that our conditional probability can be summed up like this. But the reason that I picked this example here is because of what's going on here in the denominator. You have to be very careful with these conditional probability problems to keep in mind all of the different ways that this probability of event B, so to speak, can occur. When we have the probability of A given B is equal to the probability of A and B divided by the probability of B, in this case, that probability of B represented the probability of getting a positive test result, and we had to keep in mind that there were multiple ways that would occur. There was a probability that you had AIDS and the test was accurate, and there was a probability that you didn't have AIDS and the test was inaccurate. And so there were two different ways that you could get a positive test result. So it's not enough to simply just multiply them together. You have to keep in mind all the ways that can happen. And so it's very, very important to have a lot of attention to detail when working these conditional probability problems.